Right. Here is our circle again. And we already see that if we have this radius R and our center of circle O, and then we take a little bit the theta small, but because of the purpose we make it a little bit bigger so we can see what is really this one. So this is our X from last 5 minutes ago. This is our dx. Okay, so dx is r d theta. Okay, so we can deduct the x d theta is the dx divided by r. That is our first equation. Okay, then on every point in this circle, okay, we get already this first equation, so we don't repeat it again. Okay, on every point, the velocity is always tangent. Let's say this is a point A, so the velocity is VA in modular, in magnitude. And then let's take again another point B, and this is called the VB. Okay, but in d theta as a small angle to that separate the two. This one. All right. When we replicate this VA here, let's say this is our VA, and then this is also how to work the vector. We have demonstrated if through your experiment. This must be your d theta. This must be your d theta. Okay. Right. It is same, yeah, same, because in mathematics also you learn when angle is from the same sector or same segment, they have the similar angle. Because I'm teaching IGCSE math, so I understand it very well. Let's say this is your O, but we plug it there as a vector. Cool. Then this module, they are same on every place on the circle. Right. What is this then? What is this? Who can answer? What is this? This is the difference between these two vectors. So let's say this has module V, okay, VA, and this has module VB. So this is the difference. We call it delta or dV. This is your dV. Okay, that is your dV. But be careful. Be very careful, because we are going to do approximately something, because the arc is here. And where is your dV? Your dV is this one. This is your dV. If we do this here, the red is your dV. Let me check the color so you will not be confused. This is your yellow here, but your green is this one. Let's say this is your dy as a sector. What is this? The chord. Okay, dy. If this theta is small, we can say the dy is approximately same as dv. Approximately same as dv. I don't say same as dv, but we can do some approximation. Okay, yeah? Be careful. Right. That is our approximation here, just to solve this problem. Next, d theta, this is our first equation. How can we get the second and the third equation? The velocity v is equal to meter per second. We have seen it. So it will be same as dx divided by dt. So rate of change of displacement against the time. That is our second equation. Then what is our third equation then? We already said before, A equals dV divided by dt. That is our third. Okay. I ask you to take note because I'm going to change page. So based on this 1, 2, and 3 equations, we can deduct that A is equal to V square divided by R. I need you to do it a little simple exercise by doing method of substitution. Okay, take note. Take note. I change page and then I ask someone, I allow someone to write on my screen. Please take over the screen. I allow you now. Please write. No one?
Right what?
Right what? Right. Based on those 3 equations, give the expression of A.
Wait.
Okay. I need you to write on the screen, not messaging. Write on the screen so everybody can see how to solve it. What is the first equation again? First equation?
D theta equals to dx over v.
D theta equal x divided by r. Dx
R.
divided by r.
I misread it.
Okay, number 2. Equation number 2. D theta dx divided by r, right? dv divided by dt. Okay, number 3. Question number 3. V equal
dx over dt.
Fantastic. Okay. Okay, let's do some substitution. What can you get can you replace the dx from here? Of course, yes. Okay, so dx is r
Theta
times d
equals to
theta.
Uh,
Cool?
yes.
And then you can change the dx from here.
R over
Take the dx from here. So v equal, replace that dx.
R times d theta
Okay,
over dt.
dt. What is the problem now? dv divided by dt. D theta divided by dt, right? Okay, that is our problem right now. How to find it now? Go back to here. This is our
use
d theta.
use
This
you
is our v, and this is our approximately dv. Cool? Approximately, yeah, we say dy equal dv because the dv is only this one. This one is our dy. All right. So dv equal v d theta. Correct? So our d theta here is the problem. So you will change it with this. Okay? So d theta is equal dv divided by v. Correct? All right. So we can deduct now the v here. So v becomes r times d theta, r divided by dt. Let's take it out. We multiply by our d theta here, dv divided by v. Correct? Because d theta, we have d theta here. Okay, d theta, we deduct, it is equal to d theta dv divided by v, dv by divided by v. We can take out again, r is independent, v also is independent, multiplied by dv divided by dt. Okay? Hello?
Yes, Mr. Yes.
Yes, Mr. Still here.
Okay.
Yes, Mr.
Is this v same as this v? Of course, yes, same.
Yep.
What is dv by dt? This is your acceleration, because we said acceleration is rate of change of velocity.
Velocity over time.
Okay, so v, you go here, v square is equal r times your dv by dt is equivalent to a. Okay, so a is v square divided by r. Proven. All right, all right, all right. So the difficult point is only to do the approximation like we did before. That's why, because this is our S and this is our dv, then we need to do approximation, but the radius becomes V based on what we see before. This is the key point, okay, to get this relationship here. And the V also, they are same as this V. That's why we calculate it, and then we have V square R equal the dv per dt is our acceleration here. Then acceleration means the square of the velocity divided by the R. All right. What is the second law of Newton again?
F equals ma.
F equal M
Ma. Mass times
A.
acceleration.
And F equal M V
dv over
square
v over t. Oh yeah,
R.
over R.
R.
over R. Yes. Who has something to say in the background? All right. I want you now to express the force in function of the mass, okay, the radius, and the, what is this? W? Angular velocity.
Angular velocity.
So change this formula, okay? Yes, by using in function the M, R, and W. So you can say F equal function, this one, yeah, function of velocity and the R. Okay, here, M, here. But this time I ask you to express the F in function of mass, R, and the W. Stage is yours. Change page. Go. This we have seen before, yeah? Okay, now somebody must write the F in function of mass, radius, and the angular velocity. What is the F? If you check at your book, what is the expression of V in function of R? There. Yes? Can you see my book?
I have something.
F equals to M times W square times R.
All right. There is.
MRW squared.
Right. Correct. Correct. Hello, whose dog is that?
Bark.
Barking. Ask the dog to be quiet. Bark less. Wag more.
Don't have a dog, so I don't.
MV squared divided by R. V is
Equals-
omega R. Just you need to change here. Okay, so M divided by R times the square of omega R.
Squared.
Okay, M omega squared R squared divided by R will be
Over R.
R. No la, not over R, because this is square. This, so F also can be expressed as M omega squared R, also equal M V squared divided by R. Please be aware of this one, because this also is a base of our gravitational field or dynamic of a circular motion. Okay, cool.
Cool. So cool. Super cool.
All right. Marcelino. Marcelino,
Hello, sir.
are you there?
Yes.
Marcel?
Yes, Mr.
Okay. What is the application? Maybe application of this motion, circular motion? Everyone? What? Okay, it's okay. All right.
Orbit for satellite orbit, Mr.
Yes, satellite orbit. One. That is, we go it in gravitational field. All right. Satellite. Then this
Mr.
you always
Actually,
play it.
to
This motion, circular motion, is to design your what is the game in a circle, and then everybody must get into cart, and then it will go up and down. What is that?
roller coaster.
Oh yeah, roller coaster. Yes, you are correct.
Great. Now you
Correct.
made me miss Disneyland. God damn it.
A roller coaster. Yes, it's in the book, guys. It is in a roller coaster. You need to design it like that. So what is really the philosophy behind this? Okay, in roller coaster, this is the center of the roller coaster, and you must calculate who is talking.
Sorry, it's my brother. Shut up. Okay.
Don't do that. This is your force. Okay, and this is your velocity. All right. What you need to do to design your roller coaster, guys? You must calculate the angular velocity and the radius to put the roller coaster still have this centripetal force. This is called the centripetal force. Because if this is bigger, the cart will leave the roller coaster and then you kill somebody. Because at the point the velocity of this will be bigger than the centripetal force, this cart will go off and people will sue you to the court. That's why you need to design a roller coaster. We call also what is called loop the loop. Next time we are going to check this called loop the loop. So you release the cart from this distance, from this height, okay? and the cart will go down and will face this velocity v here. Then it will go up in a circle, and then you must calculate the radius of your circle, because this point C, they will have different again velocity u. Okay, so in this case you have the mass of this cart, okay, and then you have the height of your loop-the-loop. Then at certain point P, it will have a uniform velocity just to pass here, and when it reaches this point, it will go into velocity u, and then make this pass this circle, and you must determine the r. Okay, that is called the loop-the-loop. And we play again about energy. What energy is in here? Potential energy.
Kinetic energy.
mgh, right?
What kinetic energy?
Yes, this is potential energies in here, because the V0, only the mass and the height will act, but beta, it is different here. It is transformed into kinetic energy here, right? And here will issue again potential energy and kinetic energy also, same. So it use both, because this have velocity, and in the point C it will have the maximum velocity and then drop. All right, next time we are going to solve this problem. So the point here is to determine the height you should give to the cart or your ramp, okay, in order this cart will pass here and will not go off if it reached the point C. So how to do that? Then we give a certain radius called A, yeah, radius of the path here. So what is the minimum radius and maximum height you can give to the cart, so it will not go off when it reaches the point C. So this is also R, so 2R, all right, 2R. So it will reach
That
the
means
diameter.
2R would be H.
Yeah, we determine it next time. So the H will be in function of
2R.
is called the let's say A, the maximum distance. All right.
Want to submit?
Yeah.
That is safe.
All right, guys. It will end in 5 minutes, so I thank you very much. It's okay. I stop sharing. Then quick reflection. Hello?
Mister.
Okay. One student is not here. Who is that? Who is not here? I think the same guy is called Alvin. Yeah, Alvin is not here. Yes, What happened to him again? Ask him what happened.
I have a hunch that he might have connection issues because it's happening. It's been happening to him lately.
Okay. Yeah, Alvin is not here. Second meeting. Okay, quick reflection, guys. What did you learn today?
A lot.
What?
Well, specifically, a lot more equations. We're
Mister.
talking more about radius and how it affects velocity.
Mister.
Yes.
People. That's so
Juan
cool.
has internet problem, Mister. Connection problem.
I called it.
Nicely.
Okay. Alvin had a connection problem. Anson.
Yes, you
Okay.
have a connection problem, he said.
All right. So, okay, today we wrap up things. We try to check the expression of our velocity, okay? In terms of velocity, the spatial velocity, as we know, the meter per second in function of our radius and our angular velocity. What is the unit of the angular velocity? Radian per second, okay? If we say radian per second, it means the theta in radian divided by the time. It is hidden somewhere, radian per second. So theta divided by t, or d theta divided by dt, right? The expression of the acceleration in function of our velocity and in function also of our angular velocity, and then the application of the second law of Newton to find the equivalent force in terms of V, R, and the mass of the object and the radius of the path or the circle, then expression in function of the angular velocity, of course. Okay, I'm going to end this session. Thank you very much and see you next time.